Hello, this is Samuel with the Physics Focus, and today I am going to be looking at two-slit interference, wave interference passing through two slits, and how to derive the equation, where it comes from and how to use it. Now for most A-level courses you don't need to know, as in you're not required to know how to derive and be able to prove how to derive this equation. But I think that if you understand where it comes from, it makes it a lot easier to remember it and understand how to use it. So, here we have a screen with two slits in. Distance apart, D. Here we have a single light source shining on these two slits, so the light passes through both of them. This is because we want these two slits to act as two coherent light sources, what we call coherent light sources. In other words, they stay in phase. So if they're in phase at the moment, they will always stay in phase. And the easiest way to achieve that is to shine a single light source onto them. It also helps if this light source is what we call a monochromatic light source. In other words, just one wavelength. And the best way, the easiest way to achieve that is to use a laser, which is probably what you've seen done in your school experiments. So we have this light shining on the two slits. This blue line here is just a reference line that's showing the straight ahead direction, and a screen over on the right, which will pick up the results of whatever's going on here. Now if you consider these two red lines here, two parallel red lines, this is showing the path taken by light leaving the two slits and travelling straight forward, which will then meet at the point directly in front of this double slit on the screen over on the right here. Now okay, if it's going to meet, they're not quite parallel, they're slightly convergent. But given that this distance here between the two slits, if we're talking about light, that distance is typically measured in nanometers. And the distance from the slits to the screen is typically the other side of the room, several meters. So the fact that they're not quite parallel is negligible. We can ignore that effect, and it makes it a lot easier if we assume that they are parallel. It makes it a lot easier to work out. So if these two red lines, if the light travelling along those paths starts out in phase, it will end up in phase. So at that point we'll have two light signals arriving, both going up to a trough, down to up to a peak, down to a trough, up to a peak, etc. at the same time, so we get constructive interference. We get a maximum amplitude over at this point here. Constructive interference. Okay. Apologies for the handwriting. Now if we assume that we're looking along this direction here, the green lines. Now this is at an angle theta to the original direction, let's say. Now these two green lines will travel out and meet at some point on the screen over here, and I hope you can see that the path taken by these two green lines, the upper green line has to travel a little bit further than the lower one in order to get there. How much further? Well, let's put a line across here in order to give us a right-angled triangle. Now at this point and this point, from there the two green lines have the same distance to travel. After that they're just running next to each other. Now if this angle is theta, so is this. This gives us here this small right-angled triangle, and the extra path travelled, the extra distance travelled by the upper green line is this length here, which simple trigonometry gives us. So the extra distance equals d sine theta. Okay? That's the extra distance that this upper green line, the light travelling along this upper green line, has to travel. Now, if this extra distance happens to be equal to half a wavelength, then this line here will be completely out of phase with this one when it arrives, and we will get destructive interference. If, however, d sine theta, that extra distance travelled, happens to be equal to one wavelength, or indeed any whole number of wavelengths, where n is an integer, a whole number, if that's the case, then that will give us again constructive interference. So if n is 1, that's at one whole wavelength further. In other words, it's gone right out of phase and back in again. So these two lines will be completely in phase and will give us constructive interference. Rearranging this equation slightly, this is the way it's normally expressed. If sine theta, the angle we're looking at, equals n lambda over d, that is the condition for constructive interference. So, assuming that d is bigger than lambda, then you may well be able to go through several multiples of this, so 1 lambda over d, 2 lambda over d, and so on, because of course sine theta goes up to a value of 1 at 90 degrees, which is as far as you can get in this situation before you would have to be coming back, which doesn't work. The light only travels forwards from the two slits. So this can go, take any values, any value of n, so long as it doesn't exceed 1 overall, a value of 1. So you may well have several maximum points on your screen over here. When you do this with a laser through two slits, you usually see several bright patches, a sort of series of bright fringes going across. So that's the equation, that's where it comes from, and that's all you need to be able to work out the direction of the constructive, the maximum points, constructive interference. If you want to know exactly how far away they are here, all you need to do then is know the distance from the slits to the screen and the angle, and do a little bit of simple trigonometry to work out the actual distance across. Thanks for listening.